Okay, so when writing rational functions from intercepts and asymptotes, if we have a rational function that has x-intercepts at x equals x1, x2, x3, all the way to xn, and we have vertical asymptotes at x equals v1, v2, all the way to vn, and no xi is equal to any vj, so none of these are equal, so we could cancel them out. Then we get the function f of x equals a times x minus x1 to the p1, x minus x2 to the p2, dot, 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 x minus x sub n pn, all over the same thing with v's and q's, okay? Now, the powers p and q are determined by the end behavior of the graph at the zero corresponding intercept or the asymptote, and the stretch factor a is found by using some other value and the function other than the x-intercept or the horizontal asymptote. So you could use maybe a vertical intercept or something like that. And so that would be the way to do it. So remember, if we have our intercepts, something like that, our asymptotes, that's going to be a multiplicity of 2. Whereas if we have something, that kind of comes down like that and like that, that's going to give us a multiplicity of 1. If it comes down and it touches the graph, that's going to be even multiplicity. And if it kind of comes down and goes through the graph, then it's going to be an odd. So probably 1. This might be 2. So it kind of depends on how flat or broad it is and how much, it goes through like that. But that's going to be how we're going to kind of determine what our multiplicities of the p's and the q's are up here. We'll know our asymptotes, obviously. We'll know our intercepts, and so then we just have to apply those other items that we know and get the rest of the thing. And now what we're going to do is use this to try to write a function of this graph. Okay. And so let's see here. Let's write down what we know. Let's go ahead and go back to purple. So what do we know? Well, it looks like we have a vertical asymptote. Let's use those. So we have vertical, and we have that at x equals a -2 and x equals 4. Okay. Now at those, this one indicates a multiplicity of 2. And this one, because it kind of goes down here and up here, that shows this should be about a multiplicity of 1, or an odd anyway. Then we have our intercept. We actually have an x-intercept. That's going to be at 2 comma 0. And it's going to be even, and so probably multiplicity of 2. We usually write it in the least terms if we don't know for sure. What else do we know? We have vertical asymptotes. We have our intercepts. We have a y-intercept too, it looks like. It looks like right here, that looks like we have 0, 1/2. Okay. And that's going to be our y-intercept. So I think we have about as much as we need. And now what we can do is what we're going to have to do is we're going to write into this formula and we'll have the a out front. So we actually have to solve for that a to get the final kind of function. Okay, so let's write the function as what we know now. F of x equals a times, and now what do we know? Well, we know our intercept here, so that's going to be x minus 2. So we have to kind of, take it to the other side. And it's going to be even multiplicity. So we'll call that squared all over. And then we have our vertical asymptotes. So that's going to be x plus 2. And that's going to be to the first. And x minus 4. And we said that's multiplicity of 2. Okay. So that's what we can get just from vertical asymptote, x-intercept, and the y-intercept. Okay. Now we have to solve for a. So we're going to use our x-intercept to do that. So y is 1/2 equals a, and then we're going to have plug in 0 for all those. So it's going to be a 0 minus 2 squared over 0 plus 2, 0 minus 4 squared. And so we simplify that. That's a, and that's going to be minus 2 squared is going to be a 4. Then it's going to be a minus 4 squared, 16 times 2 is 32. Okay. And so now we have basically, let's write it over here, 1/2 equals 4a over 32. And so now to get rid of that and solve for that, we'll have multiplied by 32 over 4, multiplied by 32 over 4. And so those cancel and we get A equals. Now 2 will go in here. We get 16 divided by 4 is going to give us 4 for A. Okay. And so f of x is actually going to be 4x minus 2 squared over x plus 2, x minus 4 squared. And so that would be our function of this graph. And again, all we did was we looked at the vertical asymptotes and their multiplicities, our x-intercept, the multiplicity, and we got that because, it came down and went back up. If it had came down and went through, then it would have been a 1. And then we got our y-intercept, which we needed to solve for our a, and then we were able to write our full function then after that. All right. So application. So here we have a large mixing tank. So this kind of reminds me of one earlier with the freshmen and the sophomores. Currently contains 200 gallons of water in which 10 pounds of sugar have been mixed. A tap will open, pouring 10 gallons of water per minute into the tank. At the same time, sugar is poured into the tank at a rate of 3 pounds per minute. Find the concentration in pounds per gallon of sugar in the tank after t minutes. All right, so maybe we should write two functions here and then combine them into the final function. Maybe we can have a sugar function and we can have, I guess, a water function. Okay, sugar, we have 10 pounds and we're going to add in 3 pounds per minute. And water, we started with 200 pounds, or gallons rather, and we're going to add in 10 gallons per minute. Okay. So our overall concentration, maybe we'll call it C of T, is going to be equal to what? Well, it's going to be 10 plus 3T over our 200 plus 10T. Okay. And I would leave it at that. I wouldn't simplify any further. And I would just say that would be my concentration function after T minutes. Okay. All right, so this one, it says concentration C of a drug in a patient's bloodstream T hours after injection is given by this function. Now use the calculator to approximate the time when the concentration is highest. Well, that's going to be our max, right? So let's go over to our calculator, and if we look, what we're going to do is we're going to plot that function, the 100x divided by 2x squared plus 75. And that's what it looks like. Now, really, we don't even care about this part on the left. Really, all we really care about is starting at x equals 0, because if we're doing it, we're going to add it, take a pill at time 0. It's going to go in, it's going to start increasing in our bloodstream, and then it's going to start decreasing with time. And so what we want to do is we want to find that max. Well, we just hit second calc. We want max, so we want a 4. And then we just have to go over here. Let's say that's going to be our left bound. Let's call that our right bound. And so somewhere in here is going to be our max. Okay. So the max is going to be at time 6.2, and that was going to be hours. And then the max concentration is going to be 4.08. Now it doesn't tell us what our units are for that, and so we won't know that. But going back over here now, the max time is going to be t equals 6.12 hours. And that gives us C of 6.12 is equal to 4.08. And again, whatever units are. Okay, so we'll just say 4.08 units. And again, this was really easy because we were able to use our calculator to plot it, and we were able to, again, get that time, which is what they asked for. And then we also were able to kind of get our units or our concentration, but it didn't really ask what that concentration was, but that would be that concentration at that time. All right, so now we have an open box with a square base is to have a volume of 108 cubic inches. Find the dimensions of a box that will have a minimum surface area. Let x equal the length of the side of the base. All right, so let's draw our box first. So we'll have, some height, and we'll have a base. And I'm not a good drawer again. So then it's like that. And then we'll come down. All right, so we know it's x by x for the base. It's open top, so we don't have anything up here. And, well, we'll need some different height, so we'll have that. Okay. Now, what is the volume of the box? Well, it's length times width times height. Well, volume is going to be x times h. So volume is equal to x squared h. Well, we know the volume. That's 108. X squared h. Okay. So I'm thinking we might be having to do something with that in a little bit. But first, we have the volume. Now what we need is we need a surface area. Well, surface area, we're just going to have to find the surface area of each of the sides. Now remember, there's not a top, so we have this surface area on the bottom, which is going to be x times x. So surface area is going to be x squared for the base. And then each of these sides is going to be the same because we have the base and then it's just height. So it's going to be how many of those sides? We'll have 1, 2, 3, 4 times h times x, or x times h, however you want to look at it. Okay. Now we want to minimize that surface area. Okay. So to do that, what we're going to have to do is we have to have all units the same. So we can't have an h here. So that's why we have this. And so h is equal to what? 108 over x squared. And so then we can plug that in here, and surface area is equal to x squared plus 4, and then times 108 and over x squared, and then times x. Okay. Now 4 times 108 is going to be 432. So our surface area is x squared plus 432 over x. All right. So that is then our surface area, and we want to minimize it. So what we have to do now is we have to go plot that. Now I don't have this one in, so we'll have to go and actually type that. And so that was x squared and then plus 432 divided by x. Oh, let's see, our window, let's go, I don't know, from negative 20 to 20. I don't know. I think this is going to be big because we have 432, so we better do 500 to 500 because I'm not sure where that's going to go, not 1,000. And let's go by hundreds. So let's see if we even have anything in that. All right, so we do have some. So it comes down and we have this. And so it looks like our minimum, because that's going to be, going to infinity that way. So that's not a minimum we can use, and that's going to positive. So our minimum has to be in this region here. So if we calc the minimum, 3, let's say we start there somewhere, and then it's going to go back up somewhere. And so then we come back down. So it looks like our minimum is roughly at x equals 6, and then y is equal to 108. Okay, so our min is x equals 6, y equals 108. Okay, so that's going to work. Now, if x is equal to 6, that is really the same x as this. And so we're supposed to find our dimensions of the box. So our dimensions are going to be x equals 6. So all we need to do is then find h. Well, if we plug in h, we'll have 108. 108 divided by, let's see, 108 divided by 36. That's going to give us 3. And so if we write that out, we'll have that. So our dimensions are going to be 6 by 6 by 3, and they're inches. So we can put our inches like that. And that's going to be our dimensions of our box. Okay. And again, we're able to use our calculator to get that minimum value, and that was kind of a nice feature. And so when we look for minimums, or in this case, we had the maximums, we just used our calculator, plotted it, and then we were able to use that function and actually find the value. Okay. All right. Well, let's stop there and we'll come back for more.